Hey guys, welcome into the Wells Tech Garage for this month's training class. Today we are going to be talking about the wideband oxygen sensor, or the air-fuel ratio sensor, whatever you might want to call it. That's what we're going to talk about today. Now this class is going to be kind of a continuation, or let's call it a sequel, from our last class on oxygen sensors. So if you haven't checked that out, I definitely recommend going back and taking a peek at that, because a lot of the information that applies to a narrowband standard oxygen sensor actually corresponds directly to a wideband or air-fuel ratio sensor. Things like installation tips, do's and don'ts, things that contaminate or kill sensors, that kind of thing, they all apply also to a wideband sensor. So to save time, I'm not going to get into any of that today. I'm just going to cover the operation of a wideband sensor, how they function in a vehicle, and we're going to do some testing on some vehicles. Now, guys, I wish I could stand here and tell you everything that you're ever going to need to know about wideband oxygen sensors, but honestly, unless we're only talking about a specific vehicle manufacturer, it's nearly impossible to do, because like everything on cars nowadays, everybody's completely different. I can't teach you guys the system of wideband sensors without getting specific to individual vehicles. So I have some examples. I have two vehicles in the shop. I'm going to show you guys as much information as I can to get you going in the right direction. But research and verification and looking at your code data, looking at your trouble code setting criteria, that's all going to be very important to do when we're talking about widebands, because again, they can be very, very different on different vehicles. Now, before we get into how they work and what they do, let's give away some t-shirts. So for those of you, again, who aren't familiar with this, every class we give away a t-shirt if you answer our t-shirt giveaway question correctly. So the question today is, a wideband oxygen sensor set a heater circuit trouble code, and the heater has been diagnosed and it has failed. It's not functioning whatsoever. Technician A says, this doesn't affect the sensor's operation really, it just takes longer for the sensor to heat up by using that hot exhaust gas, and it'll eventually start functioning. Technician B says the sensor will not function at all without the heater and it needs to be replaced. So who's correct? Technician A, Technician B, C for both, D for neither. Go ahead, chat in your answer in the little text box here. If you guys are watching on our website, you do have to be signed into your YouTube account in order to be able to chat in. Otherwise, if you're already on YouTube watching, you should be able to chat in there. So go ahead, chat in that answer. This is only really intended for our live audience. And if you guys are having issues, shoot me out an email. I'll bring that up later in the broadcast. And let me know what's going on. So I'll get to this in a little bit. Once we get over to the vehicles, we'll give out the answer. But honestly, guys, if you pay attention in this part, chances are you'll be able to get the answer correct by the end of the broadcast. Okay. Fuel trims number 3, the wideband oxygen sensor. First of all, the sensor has a ton of different names. Wideband, air fuel, AF, LAF for lean air fuel, UEGO for universal exhaust gas oxygen sensor, linear, AFR, I'm probably forgetting some here, guys, but the point of this is almost every manufacturer has a different name for the same sensor. It is a sensor that sits in the exhaust manifold and tells the computer what the air-fuel ratio is. Now, the point of a wideband is, I guess exactly as it sounds, it covers a wider band of air-fuel ratio. Remember, our narrowband sensor was only accurate at that 14.7 to 1 mark. Our wideband sensor will see accuracy down to like the 12.1 to 19.1, 12.1 on the rich side and 19.1 on the lean side. Now, there are some sensors and some vehicle manufacturers out there who are dipping that rich side lower and that lean side higher. But as a general idea, we're monitoring in between that threshold. So the major benefit of a wideband oxygen sensor or air-fuel ratio sensor is that it's able to look at that air-fuel ratio imbalance, any sort of issues, and it's able to almost instantly correct what's going on with that. Instead of our narrowband sensor, which are switching, and then we see our short terms start to ratchet down, on a wideband sensor system, you'll see those short terms react almost instantly right to where they need to be to bring that mixture back to lambda or stoichiometric or 14.7 to 1, whatever it may be on your scan tool. Okay, so that's the basics of a wideband. So why do we use widebands? Well, with increasing technology and increasing emissions standards, we need to have a faster, more accurate way to measure our air-fuel ratio. In comes widebands, and they can react to changes in the air-fuel ratio around 100 milliseconds or 10 times per second. We might be able to see that reaction of the sensor reacting to air-fuel ratio. Now, I'm sure there's some sensors out there now on even newer vehicles that are reacting even faster. This might be an old, out-of-date number. The major, biggest, hugest benefit, most huge, benefit is instead of the narrowband sensor having to switch back and forth and the computer ratcheting those fuel trims, the sensor is able to immediately do it and know exactly how rich and lean it is. So it's not guessing that it's just lean somewhere above 14.7 to 1. No, it knows exactly that it could be 18.1 to 1 or 17.7 to 1 or something like that. It's able to know precisely where that air-fuel ratio is at that exact moment. So by controlling this accurately and quickly, we're able to decrease our overall vehicle emissions. Here is a data graph right off the scan tool of a pair of air-fuel ratio sensors on a, I believe this was our 2003 Lexus that we have in the shop. Now you can see we have some differences here, right? We're looking at AFS voltage, bank 1 sensor 1 and bank 2 sensor 1. And they look completely different than a narrowband sensor. And this is normal. This is not going to look like what you guys are expecting to see when you're looking for oxygen sensors. Air-fuel ratio or wideband sensors are typically going to be a flat line or much more flat than a switching constant back and forth sensor. Okay? So this would be a normal operating air-fuel ratio sensor PIDs on our 2003 Lexus that we have in the shop. Okay? So I wanted to show you guys that. Now here is some PIDs off of a 2013 Honda Pilot. So as you guys can already tell, we got quite a few PIDs here. You know, maybe with a narrowband sensor we're used to 4 or 6 or maybe even 8 PIDs. Well, you can tell we got a lot more information being told to us by the scan tool, by the computer, about what is going on with these sensors on this vehicle. And now these are only the air-fuel ratio sensor PIDs. Now if I add in both of the post-CAT sensors, which are normal oxygen sensors on this vehicle, we would have even more PIDs. These are only referring to the air-fuel ratio sensor PIDs. And actually that brings up a good point. Air-fuel ratio sensors or wideband sensors are typically only going to be the pre-CAT. So the bank 1 sensor ones and the bank 2 sensor ones are typically the air-fuel ratio or wideband sensors. Typically the sensor 2s, so bank 1 sensor 2, bank 2 sensor 2, will typically be still a standard oxygen sensor, standard narrowband oxygen sensor. I don't know of any vehicles right now that are running 4 widebands on them, but it's possible. If you guys know of one that's using 4 widebands on it, let me know. I'd be curious to know what's out there. But like this 2013 Honda Pilot here is running 4 sensors in total, but it's only 2 widebands and 2 narrowbands on there. Okay, and that's pretty typical for the modern day vehicle. So the need to know about widebands. Well, first of all, they look very similar to a narrowband sensor. You know, you got a wire harness, a connector, and a sensor element that gets, you know, threaded right into the exhaust. Same story of a narrowband sensor. Don't mistakenly put the wrong sensor in. It's possible it might even plug into the connector, and this is still going to be the same size hole that it's going to thread into. So it's possible to accidentally install a narrowband sensor in a wideband sensor's hole. Just be careful, make sure you get the right parts, otherwise you could you could really create some issues. Our good friend Eric O from South Main Auto actually has a video on this where he's looking at air-fuel ratio sensor on a Honda where somebody did just that. They installed a switching narrowband oxygen sensor, and he had to have the fun of figuring that one out, because I believe in his video it wasn't setting any codes, so crazy. But don't accidentally put the wrong sensor in. All right, wideband sensor can be represented in many different ways in our service information and our scan tool data's information. we might see it represented as a milliamps PID, a voltage PID, an EQ or equivalence ratio PID, or a lambda PID, okay? We're going to see different ways for these sensors to be represented. This is key right here. There's no general rule of thumb for widebands. Again, every manufacturer is kind of doing things differently with their voltages, their inputs, their grounds. They're all kind of doing it different. So we can't just throw a rule of thumb at it and say, on the signal wire, you should see 2.5 volts. I can't say that because that might only be equivalent or might only apply to one manufacturer. So every vehicle manufacturer is going to be a case-by-case diagnosis, guys. You have to do your research, and trouble code data is going to be key for this. You get your code, look at that code set criteria, look at that data, see if you have some values in there that the computer's testing for, then you can look for the same thing. You know, duplicate the problem. All right, a scan tool is necessary to diagnose most wideband sensors issues. Completely true. Wideband sensors are going to be very, very, very hard to diagnose not using a scan tool. And I'll get into that in just a couple slides here of why that is. And then on your scan tool, a lambda or EQ or equivalence ratio PID on an engine using wideband sensors is typically representing a real-time air-fuel ratio. That same PID on a narrowband sensor motor is going to be typically represent the commanded air-fuel ratio. So keep that in mind. Lambda or EQ on wideband is real-time air-fuel. Lambda on a narrowband engine is typically commanded. Wideband heaters. So just like a standard normal load narrowband sensor, the widebands also have a heater built in, but heaters are absolutely 100% critical to sensor operation on a wideband sensor. A faulty heater is a faulty sensor, period, end of story. The heater fails, sensor's not going to operate. Not like a narrowband where it just might take longer to become responsive. It's not going to work. Temperature on these things is much, much greater. We're talking 13 to 1500 degrees Fahrenheit. And changes in that temperature affect the output values of the sensor. So the computer monitors, the PCM monitors the temperature of the sensor and maintains a specific temperature, a specific temperature of what it wants to see. And that way the signal coming out of the sensor is accurate. So that temperature can affect that. Computer's going to maintain that. Typically we'll see a 12 volt power source in, constant, probably from a fuse, and then the computer will pulse width modulate the ground side. Typically a cold sensor, you're going to have a higher pulse width to get that sensor up to temp, and then you'll see that scale back as the sensor gets hot. PCM then just tries to maintain that, let's say 1500 degrees, okay? So heaters, absolutely critical and much hotter. If the heaters failed, sensors failed. Okay, different widebands. Now, like I talked about, each manufacturer kind of has their own deal. Well, they kind of have their own deal with two different styles of sensors. So let's say, let's just call it this. We have two different styles of sensors, and manufacturers use one style or the other, or the best way is to do your research. But let's talk about those two different styles. So first of all, you have your single cell wideband. This is typically going to be 4 wires. So this is one of those circumstances where you could accidentally swap in a narrowband sensor for a wideband if you're not paying attention. So 4 wires, 2 typically for that pulse width modulated heater circuit, so our 12 volts in, our pulse width ground, and then 2 for the signal circuit back to the PCM. Scan tool data, again, is going to be super important. And again, you need to know if you're using generic data or enhanced scan tool data. Now, a lot of our full function, high-end scan tools are going to give us some enhanced data, but I just want to bring this up. Many of the OE diagnostic procedures that you look into for wideband sensors say they require the factory scan tool. And the reason why that is because of a little thing that happened back in the 90s with Toyota. So scan tool data on a Toyota from the 90s used to look like this. On a 4-wire sensor, you would see your voltage reading here, 0.5, 0.6, 0.66, 0.7, 0.8. You would see a value like that. Now, if you were to graph that out, it would remain pretty steady because it's an air-fuel ratio or wideband sensor, right? But say you didn't know exactly what you were looking at, okay? Say you were maybe didn't know that your 99 whatever Toyota car had a wideband sensor in it. You throw a scan tool on it, and you see it sitting steady at 0.66 volts, okay? Well, you have an air-fuel ratio, or you have a code in there for an air-fuel ratio or wideband sensor, and you're looking at this thing, and it's just remaining steady. But what you don't realize is that is actually perfect. I mean, 14.7 to 1. That engine's running perfect. But, you know, you want to be proactive. So you're going to go out there and you're going to try and change the way this thing is running to see if your sensor moves, right? So you take a vacuum hose off, create a vacuum leak. Narrowband sensor, you should see that voltage drop, right, down to that 0.1, 0.2 mark. Well, if you do that with this sensor, you're going to see a 0.8 volt mark at 18.5 to 1. So as we go lean, our voltage actually goes up, which is completely the opposite of what we're used to with narrowband sensors. And this is where the confusion came in by people trying to manipulate the sensor to make it react to something and it doing the opposite. So at this point, does it need a sensor? Are you throwing a computer at it, maybe some wiring, something like that? You don't know without knowing the enhanced data. So this data was kind of confusing, you know, 0.5 volts. If you run this engine rich, you would expect to see 800, 900 millivolts. Well, you run this engine rich, you're going to see 0.5 volts. So what happened then is we were granted enhanced scan tool data. So if you put the Toyota scan tool on this, if you put a full function tool on it, you're going to see completely different values. So instead of 0.66 volts, you're going to see 3.3 volts. Well, right away, that's telling me that I don't have a narrowband sensor in there, right? I already know that I have 3.3. That's not normal. It's not 0 to 1. So I'm not thinking the same way that I would be thinking if this was a narrowband, okay? And then I run it rich or lean, and it's going to respond accordingly. So the reason why this generic scan tool data is in here is because back in the early days of OBD2, it was mandated that your O2 sensor PID information was between 0 and 1 volt, okay? So when Toyota and Honda, which were the early adapters of air-fuel ratio or wideband sensors, when they decided to put these on their vehicles, they had to conform to this mandate, right? So their sensor wants to operate between 2.5 and 4 volts to read your 12.5 to 1 to your 18.5 to 1. So what they did is they just took their enhanced data here and divided by 5. So that's where you get 0.5 volts for 2.5 and 0.8 volts for 4. So it gets confusing. Eventually, the OBD2 mandate was kind of lifted or amended so that the enhanced data could be shown in there. The voltage differences could be shown, but just keep an eye on that. Depending on what scan tool you use, generic data like this can kind of screw you up, so be careful. Okay. Here is a wonderful drawing of a 4-wire wideband sensor. Okay, this is something that I drew up. Again, we still have our zirconia element in the center. We have our reference air and we have our exhaust gas, right? Just like a narrowband sensor. We have some platinum electrodes surrounding our zirconia, and we have this diffusion layer here, okay? So the whole point of this sensor right here is to maintain this platinum electrode at stoichiometric, at 450 millivolts, all right? So there's going to be a difference between these two chambers right here, between the diffusion layer and our reference air. So there's going to be this difference. It's going to create voltage. We want that to be 450 millivolts, or, you know, perfect stoichiometric, 14.7 to 1, right? So what the computer is going to do is it's going to pump current in or out of these electrodes, and what that's going to do is it's going to create this chemical reaction, and it's going to move these ions across our zirconia element. It's going to move some oxygen, okay? So if we're reading rich exhaust, okay, we're reading a lack of oxygen inside of our exhaust, we are going to control this pumping circuit. We're going to add some current to it, and we're going to make these ions, these oxygen ions, travel across here to bring that back to a stoichiometric mixture, okay? The whole goal of this thing is to maintain 450 millivolts right here by pumping oxygen across that zirconia element to maintain that, and then the computer monitors that milliamp reading, positive or negative, and the level of it. So if it's 0.5 or 1 milliamp, something like that, that's going to directly relate to a rich or lean condition, okay? So by knowing positive or negative is going to be rich and lean, and the level of how high it is rich or lean is going to be by that milliamp reading, okay? So I'm going to demonstrate this on our Lexus once we get there. It'll make more sense once we get that far. Okay, here is a 2010 Lexus RX 350 that I have a wiring diagram from, and I just wanted to show you guys what it's going to look like on a diagram. You're going to have your HA2A. This is going to be our heater control circuit. That's going to be that pulse width ground. Then we have our battery positive, which is, you know, just our voltage in for the heater. And then we have A2 minus and A2 plus. A2 plus being 3.3 volts, A2 minus being 3 volts. Okay, so what exactly do we have here? We don't really know by just looking at this. We have to do our research to figure out what exactly it is we're looking at in this diagram. So upon research, looking at Toyota service information, it tells me that our air-fuel ratio sensor generates voltage that corresponds to the actual air-fuel ratio. Perfect. The sensor voltage is used to provide the ECM with feedback so that it can control air-fuel ratio. The ECM determines the deviation from stoichiometric air-fuel and regulates the fuel injection duration. If the sensor malfunctions, the ECM is unable to control air-fuel. So basically, sensor voltage is telling the computer how rich or lean, and it's going to control our pulse width of our injectors. Simple enough, right? But there's this asterisk right here. And what that says here is the air-fuel ratio sensor is a current output device. So what the heck? It says here, air-fuel ratio sensor generates voltage. And then it says here, the air-fuel ratio sensor is a current output element. Read your service information. This sensor is a current output element. Therefore, the current is converted into a voltage inside of the ECM. Okay, that's very important, inside the ECM. Measuring the voltage at the connectors of the air-fuel ratio sensor or connectors of the ECM will show a constant voltage result. Okay, let that sink in for a moment. They're telling us the computer is taking a milliamp reading, converting it to voltage inside of its own PCM, meaning we cannot hook up a voltmeter, we cannot hook up a lab scope and monitor the voltage on this thing. It's not going to tell us anything because there's a conversion happening inside the PCM. So if I were to take a scope and put it across these pins, sure, I would see 3.3 volts here, I would see 3.0 volts here, but I could run that thing rich or lean all day, and those voltages would never change. But what we'll see is we'll see a difference in our voltage reading on the scan tool. So that's confusing. The scan tool is going to tell us that we're maybe reading 2.9 volts at that exact rich or lean moment, but our lab scope's still going to only read 3 and 3.3. So I'm going to demonstrate that, guys. I'm going to show exactly how that happens on this Lexus because it is confusing and it's kind of frustrating that it tells us that its sensor generates voltage and then it tells us again that the sensor is a current output element. So keep that kind of stuff in mind when you're diagnosing these things, is they can be tricky. It can really throw you for a loop, okay? All right, then we got a Honda Civic here, kind of a similar setup. Our power wire in, our pulse width ground, our sensor input, and our sensor ground. So our sensor input ECM voltage, 2.2 volts. AFS minus is going to be sensor ground, 1.8 volts. So you're starting to notice some sort of voltage trend here. When it comes to the ground wires on these things, they're not going to be at 0 volts or chassis ground. We have to pick these sensors up off of that ground mark and give them a floating ground or a reference ground or a computer ground or a sensor ground or whatever they want to call it. It's going to be off of 0. So Honda on this 08 Civic Hybrid is going to run sensor ground at 1.8. Lexus on this 2010 RX 350 is going to run sensor ground at 3 volts, okay? We have to pick that up off of chassis ground to take any sort of interference out of these things. They are very, very sensitive, so that's why they're not on chassis ground. So if you're testing and you're getting weird readings, remember you need to be using the sensors ground, not chassis ground, okay? Here's some Honda service information. I wanted to bring this up as a little laugh because they didn't really tell me anything that I didn't already know. They show an element with some heater terminals and sensor terminals, and they say the air-fuel ratio sensor operates over a wide air-fuel range. Sensors installed upstream of the converter and send signals to the ECM PCM, which varies the duration of the fuel injection accordingly. Doesn't really tell me anything, unfortunately. So again, on something like this, guys, you're going to have to look at your trouble code set criteria. You're going to have to look into that kind of stuff and see if you can find some of that information out there, okay? So 4-wire wideband rules. Well, first of all, there is no rules. There's no, nothing that I can just tell you guys, every 4-wire wideband is going to operate this way, right? You need to treat every manufacturer, every vehicle, every sensor as a new diagnostics. 0% or 0 milliamp current flow is ideal. That is going to be your stoichiometric or lambda mark. So zero current flow on, I believe, all of the 4-wire widebands will be stoichiometric. The sensor has to be hot. If the sensor's not functioning, if the heater's not functioning, the sensor doesn't function. Current positive or negative could mean rich or lean, so this could really throw you off. You're looking at your scan tool, you see your milliamps reading. On a Toyota, positive milliamps means the engine's running lean. On a Honda, positive milliamps means the engine's running rich, okay? So keep that in mind. We need to know what we're looking at, okay? Remember, you can always trust lambda. Lambda's not going to lie to you, so if you're showing a 1.2 on lambda, it means the engine's running lean. If you're showing a 0.8 on lambda, it means the engine's running rich, okay? And then you can watch how the wideband reacts with that. So that might give you an idea of how that wideband's reacting. Okay, fun fact, Honda's ULEV, or ultra-low emissions vehicle, 2.3 liter back in 2001, was able to support fuel trimming for individual cylinders with 4-wire wideband sensor and a special exhaust manifold design. So we talked about that last class a little bit about how nice it would be to be able to trim each cylinder individually, because sometimes you have a single cylinder deviation that you want to correct for. Well, on most vehicles you have to correct the entire bank. Well, that can take a problem that maybe wasn't that bad and make it worse. Back in 01 already, Honda was able to do this and trim each cylinder individually. So, cool little fun fact. Okay, our dual cell or pumping cell wideband. Now this is probably going to be more common today. We'll see this on most of our newer vehicles. It's typically going to be a 5-wire sensor. I got 5 wires right here. An external air source is not always going to be required. So for you guys that are into off-roading or whatever, where you could possibly contaminate your sensor, these are not going to require an external air source on all of them. That's not the case for everything, but I know for example, a Ford does not require an external air source. Again, it needs to be hot. Always look at your wiring diagrams, etc., service information to get exactly what you need to know about that sensor. Again, reference low or ground reference is not chassis ground, and a scan tool may use milliamps voltage or lambda to represent the signal for the wideband sensor. Here is a cool little drawing, I guess, of a 5-wire or dual pumping cell wideband that I drew up, okay? So we have our PCM over here, we have our sensor over here, and the connector for the sensor over here, which is very, very important on these sensors, okay? So let's start with our heater element. We have battery positive in, goes across our heater, goes to a pulse width ground from the computer, maintaining our sensor around that 1500 degree mark, okay? Then we have a pump cell, measurement chamber, a nerd cell, and a reference oxygen chamber, okay? So exhaust flows into our measurement chamber. Just like on a narrowband sensor, we have exhaust flowing in, okay? And there's going to be this voltage differential across our O2 sensor, right? On a narrowband. Well, that's what this is right here. Our nursed cell inside of here is essentially a narrowband sensor, right? So the whole goal here is for the computer to maintain this at 450 millivolts, okay? So the computer's going to do everything that it can to keep this oxygen sensor, narrowband sensor inside of here at 450 millivolts. So how does it do it? It sends current flow down our pumping milliamp wire here, positive or negative current flow, into our pump cell. That cell then, just like on a 4-wire, will transfer oxygen ions in and out of our measurement chamber to maintain that 14.7 to 1 mixture in there. The computer will then monitor how much current it's sending, positive or negative, and that'll determine exactly how rich or how lean the engine is, whether it be an 18 to 1 mixture or a 12 to 1 mixture, okay? So 5-wire sensor, 450 millivolts, it's trying to maintain that, pumping current back and forth. Now, the reason why a connector is super important on these sensors is most of them have this thing called a trim resistor right here. This resistor is built into the connector, and it's in there to accommodate for discrepancies in manufacturing, okay? So there's going to be a trim resistor in there, and almost all of these connectors have them. And that is also the reason why you'll typically see 6 wires going into the sensor and only 5 coming out. So 6 wires from the PCM, 5 coming out, right? And I can show you that here. We have 1, 2, 3, 4, 5 wires out, 6 wires in. Well, one of those pins, this pin right here, is tied to our current trimming resistor, and this is pin 2 right here going out to the sensor, okay? So this is why we have 5-wire sensors with 6 wires going to them. It's not going to be that you got the wrong sensor or something like that. Somebody didn't chop a wire off of it. That is common to happen, and that's just to make up for manufacturing discrepancies, okay? So common to happen. Not all PCMs will have that 6-wire going to it. Some do, some don't, okay? Here's some examples. Here is a 2013 Taurus, which we have in the shop right over here. We're going to do some testing with. You can see all 6 wires are here. 1, 2, 3, 4, 5, and 6 going to our sensor. So they're monitoring the current trim resistor, okay? And you can see we have all our pins laid out here. I wanted to really talk about our ground reference. It's actually 2.4 to 2.6 volts on this sensor. So again, not chassis ground, not 0 volts, not our normal ground. 2.4 to 2.6 is normal on a 2013 Taurus, okay? Then we have our 2010 Accord 3.5 here, and we have 1, 2, 4, 5, and 6. So we're skipping wire 3, and that's because the computer isn't monitoring the trim resistor on this vehicle, okay? So sometimes you'll see 5 wires, sometimes you'll see 6. Again, look at your service information, please, please, please. Figure out what you have in front of you on the vehicle that you're diagnosing, okay? So Ford was very, very nice in giving us a lot of information about their universal heated oxygen sensor. Now, you hear universal and you think, okay, well that's kind of weird. Is this one that I got to wire up? No, it's not the case. That's just what Ford calls it. They also call it a UEGO sensor. And I'm just going to read off some of this. I'm not going to read the whole thing. But I want to talk about this because Ford really shared a lot with us. It says that it uses a typical O2 sensor combined with a current controller in the PCM to infer air-fuel ratio relative to stoichiometric. This is accomplished by balancing the amount of oxygen ions pumped in or out of the measurement chamber within the sensor. The typical HO2S within the universal HO2S detects oxygen content of the exhaust gas in the measurement chamber. The oxygen content inside the measurement chamber is maintained as stoichiometric air-fuel by pumping oxygen ions in and out. As the exhaust gas gets richer or leaner, the amount of oxygen pumped in or out changes, and that is what gives us our air-fuel ratio. The measured air-fuel ratio is actually an output from the current controller in the PCM and not a signal that comes directly from the sensor. So just like on our 4-wire on our Lexus there, you can't just throw some test equipment on here. You got to look at your data information. So just like I talked about in our graph here, we have our standard oxygen sensor, our nurse cell, trying to maintain that stoichiometric 450 millivolts. So we're going to pump oxygen in and out of our measurement chamber, and that's going to change our current flow right here, positive or negative, and then our level of current flow, whether it be 0.5 milliamp, 1 milliamp, 2 milliamps, whatever it is, will have a direct relation to the air-fuel ratio, okay? It also says here this universal HO2S does not need access to outside air. It will actually pump small amounts of oxygen ions from the measurement chamber into the reference chamber, okay? So no needed reference air coming in from the outside. And again, part-to-part variance is compensated for by placing a resistor in the connector. The resistor trims the current measured by the current controller in the PCM. So Ford connectors will have that current trimming resistor inside of them. Last line here, the O2 sensor is embedded with a heater that allows quicker closed-loop activation as well as maintaining the temperature that it needs to be at, okay? Another cool thing that Ford did is kind of like Honda did back in 01. They have an air-fuel ratio imbalance monitor that estimates the difference between cylinder and cylinder using the front universal heated oxygen sensors on both banks. It's going to look at a bunch of engine revolutions and figure out a signal of the pulses going past that sensor from bank to bank, and it's able to notice deviations in each cylinder and trim each cylinder accordingly. So kind of cool that Ford's doing it now as well. And then this bottom little box down here, guys, is just something I pulled out of the service information. that is for the ground reference or ground voltage level of that ground. So you'll see here our 2.0 Taurus is going to read that 2.4 to 2.6 volts on the ground reference wire, okay? Here we have our 2010 Accord again up on the screen. I just wanted to call out what some of the pins did. So you can see all these pin values. Now, it didn't tell us anything here. We have sensor input, sensor input. Where I found this information was actually going through the PID information out on the service info. You can find a graph sometimes that looks like this. Pin number 14 right here says with engine warmed up and running, 3.4 to 4.8 volts. So pin 14 right here, sensor input, 3.4 to 4.8 volts. When I tested it, I was reading 4.05. Our reference voltage on here, so our ground voltage is going to be 3.4 to 4.8 also. I tested it at 3.5. Our sensor input is 2 to 5.6 volts. I tested it with a varying 3 to 4 volts. So that moved with differences in the air-fuel ratio, okay? Now what I think is interesting here is if you do the math between our, let's call it our signal and our ground, right here between these two pins, between 4.05 and 3.5, what does that come out to? 450 millivolts, right? So the computer's watching this right here for that 450 millivolts, and it's changing the current on this wire right here to pump those oxygen ions in and out to maintain that 450 millivolts, okay? So that's a 2010 Honda. So wideband sensors and fuel trims, okay? So that was how a single cell and a dual cell sensor operate. Make sure you do your homework, make sure you do your research on the vehicle that you're working on, but that's basics of how those sensors function. Now let's talk about how they function with our fuel trims. So a wideband sensor, you might not see your percentage values anymore. You know, we talked about like that plus or minus 10% to set a code type of thing. You might not be able to see that anymore. Your research will typically reveal what you're supposed to see on the scan tool. And you can look into code set criteria for like a lean code or a rich code. That's typically where you can find that information. So let's take a peek at some data that I captured here. So we have on top our long-term fuel trim and on the bottom our short-term fuel trim. And you can see that our numbers are just completely different than what we're used to seeing. Long-term current is at 0.93 with a max and a min of 0.93 and 0.92. Our short-term fuel trim is currently where our cursor is here at a 1.47, but we saw a swing between the minimum of 0.69 and the maximum of 1.47. And you can see a bunch of changes in here. I was actually manipulating the air-fuel ratio on this engine. Here we add in two more graphs. We can watch the air-fuel ratio lambda, or our air-fuel lambda right here, increasing, plus and minus of 1. And we can look at the milliamps on our sensor, so our pumping current, how all this works, okay? So our lambda right here where our cursor is was reading at a 1.7 lambda mark, okay? So what does lambda 1.7 mean? That means we're running lean, right? Lambda is high, above 1, we're running lean. What does our air fuel sensor milliamps do? It goes negative on our current, negative 0.43 milliamps on our current. And what does our short-term fuel trims do? They spike up 1.47, and they stay there until the vacuum problem is corrected, okay? And you can see that by the demonstration of the map sensor here with our voltage. You can see our voltage spike up when I pull the vacuum hose off. And you can also see our air-fuel ratio PID right here spike up as well. Where our cursor is sitting, we're at a 25.1 to 1 air-fuel ratio. So this is telling me our short-term fuel trims are reading a 1.47 at a very, very lean mixture. So what does that mean? Again, did some research. Honda Service Information says, and I'm not going to read this whole thing. If you guys want to read it, go ahead. But I'm just going to read this part right down here. When long-term fuel trim is higher than normal, which is about 1 or 0%, the amount of injected fuel must be increased. Well, obviously, that's the way that our fuel trims work, right? And when lower than normal, it must be decreased. If long-term fuel trim is higher than normal, it's too lean. Now, that normal malfunction threshold, long-term fuel trim is higher than 1.25 or 25%, okay? So we're adding 25% on our short term if we're reading a 1.25. So if we go back here, we were currently reading a 1.47, so let's call that 47% then, right? So 47% positive short term means we're running incredibly lean and we want to add in more fuel. So it's still reacting the same exact way that we're used to, the numbers just look different. And rich is going to be the same way. When it's lower than normal, it must be decreased. If long-term fuel trim is lower than normal, it's reading too rich. Our malfunction threshold here, long-term fuel trim is lower than 0.8 or 20%. Now, I thought this was kind of interesting. The thresholds are different, rich to lean. This engine is more sensitive to rich concerns than it is lean. So it's allowing a positive, let's call it a positive 24%, won't set a code, but a negative 20% or negative 24% will set a code for rich, okay? So if we look at our, let's go back to this one. Currently we're reading 1.47, so let's call it 47% lean, okay? When we're reading this 0.69, that doesn't mean we're running 69% lean, okay? Don't get confused here. We're starting at 1, not at 0. So we have to subtract from 1. So that would actually be roughly 31% lean or so, okay? Excuse me, 31% rich, okay? We're subtracting 31% fuel, okay? So start at that 1 mark. When it goes below that, we are taking fuel away. When it goes above that, we're adding fuel on our fuel trims, okay? So some closing thoughts on our wideband sensors. Again, I can't really give you guys a lot of rule of thumbs here or system operation because every vehicle is so different. You're not always going to find the information that you need to diagnose these things. Like we saw with that Honda sensor, we didn't have a ton of information on it. So what do you do if you don't have the information you need? Well, there are going to be a few things that you can do. First of all, verify your heater's operating. Remember, if your heater doesn't function, the sensor doesn't function. Throw an amp clamp on it and check if it's operating, right? See if it's pulling amperage. It should look like a square wave because the computer's pulsing it, okay? You could potentially swap bank 1 and bank 2 sensors, okay? If it's a 2-sensor engine, swap them over, see what happens, see if the code travels. Pull out the sensor and look for contamination or damage to the sensor, just like a normal O2. They can be contaminated, coolant, oil, all that fun stuff. And these things do wear out. They're still in the exhaust stream. They're still not going to last the life of the vehicle. And then last but not least, we have to trust our computer, okay? Wideband sensors will fail, and when they fail, the computer has way more tests and way more codes for a wideband sensor than they do a narrowband sensor, okay? So chances are if you're getting a code for it, it's probably for a reason. I wouldn't say throw a sensor in it, but let's look at some data, let's look at some PIDs, and try and figure out what's going on with this thing, but we do need to trust our computers, okay? So with that being said, our next class is going to be fuel trims number 4. We are going to finally after months here, we're finally going to fix the GTO, show you guys some tips and tricks and processes for figuring out rich and lean conditions and that kind of thing. So that's going to be next month in April. But for now, I think it's time to head over to our Lexus and our Taurus and hook up scan tool, scope, amp clamp, and demonstrate some of these processes and tests that we showed right here. We're going to manipulate some sensors and see what happens, okay? So Fritz should have everything hooked up over there, so I'm going to head on over and let's see what we got. Hey, Fritz.
Hey, Mike.
All right, you're not snoozing over here. Hopefully nobody else is. I know it's kind of a long-winded explanation on how everything works, but again, we got to kind of know the system before we can diagnose it, right?
Got to give them all the information they need.
All right, well, hopefully you guys are all paying attention because now we're going to apply it. We're going to test on our 03 Lexus RX 300 3-liter V6 in there, and then our 13 Taurus 2-liter turbo GDI motor. So why don't we just get right into it because we got a lot we want to show.
Sure.
So for starters, guys, I have a wiring diagram up on the screen here. If we just take a peek, I'll show you guys, whoa, zoom it back out a little. I'll show you guys where I'm hooked up right now. And right around here, if I, oh, there we go. So here is our bank 2 sensor 1. This is the sensor that I'm hooking into. So we're going to start with AFL plus and AFL minus, and if you remember from those Toyota diagrams, you should be seeing 3.3 volts and 3.0 volts on these two lines. And then I also have a connection at the heater control side here, and then I also have an amp clamp around it as well. So we're going to be looking at 4 different channels on the scope. So why don't we just start off on the scope since we're already talking about it. And I just wanted to bring up something interesting. And channel 1 and channel 2 here, so blue is channel 1, red is channel 2, and the key is just on right now. So it's just ignition on, engine not running. This sensor is already sitting at that 3.3, you guys can see there, 3.3, and 3.0. Again, 3.3, 3.0 volts. So just key on, the sensor is reading that 3 and 3.3 volts. So right away, without even firing up this engine, we're able to verify that the computer is sending out the voltage that it's supposed to be doing. So it's kind of a good first check. From there, we can go ahead and fire this thing up, and I'll show you guys that these numbers aren't going to move no matter what we do. So let's do it.
Let's do it.
Let's fire this thing up, and again, we're on the Bank 2 Sensor 1 air fuel ratio sensor on this 03 Lexus. All right, so we had a little glitch in there. In fact, let me stop this quick so I can show you guys that. Right here, we had this glitch going on, and that's just from cranking voltage and stuff. That's going to be just a little glitch here. You just want to ignore this kind of stuff. Cranking does some weird things to the electrical system. So we'll bring this back. We're idling now. The engine's idling. It's purring really nicely, and we're still sitting at 3.0 volts and 3.3. Okay? So we're right where we need to be. Now, why don't we add in the scan tool to this, and I'll show you guys what we have for scan tool information. So we're going to start with just going over some of the PIDs. If we want to just bring this up full screen first, Dave, so I can show them all the PIDs that we have. I'm just going to go into our AFO2 sensor data. There we go, thank you. And as soon as it loads here, we're going to be able to bring up a whole bunch of information here. And you can see we can scroll through this a little bit. So we have quite a few PIDs here. Some of it related to what I want to look at, some of it not. So what I want to look at now is just things related to our Bank 2 Sensor 1 that's going to help with our diagnostics. So I'm going to go into our custom graph, take all this out of here, and I'm going to go to, let's go short-term field trims, long-term, oh, sorry, that's Bank 1. Let's go Bank 2. And then let's grab Bank 2 percentage, Bank 2 voltage, and we can grab this, I think that looks pretty good. You think we need anything else?
I don't think so.
All right, we'll go with that for now. And I'm gonna go ahead and throw these in graph view right away. And there we go. So we got some information here. AFS heater and AFS test, just showing if it's complete or incomplete. So I'm gonna take those out. We don't really need those. So take that out, go back to graph. Try and clean up our screen a little bit. Okay, short-term field trims, long-term field trims. And it looks like we're in a percentage value. So that's kind of nice. It's looking kind of like we're seeing less than a 1% value, so it's able to determine fuel trimming at less than 1% of a change. Our AFFT Bank 2 S1 in percentage, this is looks like it's going to be our lambda value of where the engine is currently running. And then our voltage, Bank 2 S1 voltage. So just like I was talking to you guys about with Toyota scan tool data, this is exactly what I mean. Our voltage is changing on there, just like we expect it to, right? Just like I showed you guys in that graph. But our voltage isn't changing on the scope. In fact, let's bring them both up on the screen here, and you'll be able to see on our lab scope, we're still at that 3 and 3.3 volts right there, okay? Nothing's changed here. This is still perfectly straight. But then look at our scan tool here. Our voltage is varying. All right. Now, Fritz, could you go mess with this thing for me?
Sure,
Let's,
be happy to.
Let's manipulate the sensor a little bit. Let's see if we can run this thing rich or lean. So what are you going to do here?
First thing we're going to do is just give it a little vacuum leak.
Okay, a vacuum leak, it's going to get excess air past that sensor, so we're going to have excess oxygen. So we should see our sensor react. And immediately it did. All right, let's get them back up on the screen. And you'll see our lab scope, nothing happened, still reading perfect. But now look at our system, okay? Our short terms, almost an immediate spike. Look at our voltage. It spiked high up to 3.44 volts was this spike right here. Then our short terms reacted and brought our AFS voltage back down to that 3.2-ish mark right in there. Now go ahead and hook that hose back up, Fritz, and we should see the opposite thing happen. We should see our field trims come back. We should see a spike in the opposite direction as our short terms come back. So perfect, that looks awesome, okay? But look guys, did you see anything on here? Absolutely nothing changed with our 3 and our 3.3 volts. So that's the point of this whole thing, guys, is we can't be putting an ohm meter on, or a voltmeter on here. We can't be putting a lab scope on here because our signal wires coming from the sensor, between the sensor and the computer, are doing absolutely nothing for us. All right, so let's unhook that again and let's add in some fuel this time. Let's run her rich. So our voltage spikes because we just went lean. Our field trims adapt, we're running lean, and now Fritz is going to add in some propane into this thing and we're going to swing it back rich. So as the short terms are adapting, we see our voltage for our sensor come right around that 3.2 mark again, okay? And if you remember, like our short terms from last time, we would see a lot of ratcheting happening here. Now go ahead and shut the fuel off, Fritz, and let's watch how fast this thing is going to react. So all of a sudden, boom, it recognizes that it's missing fuel. It all of a sudden went lean. Look at how fast this reacts. There's none of that ratcheting happening anymore. It's not taking any significant amount of time. It's happening near instantly. And that's one of the most awesome benefits of a wideband sensor, is how quickly these are able to react. And why don't we go ahead and fix that vacuum leak. And he's going to plug that hose in, and as soon as it's plugged in, the idle just changed. Our short terms drop back down to 0. And our voltage is right back around that 3.2 mark. So right there, that's telling me that everything on this engine is running normal. Now the only thing that I think is interesting about this is this PID right here, long-term field trims. It's taking kind of a little bit of time to react, and I thought that was kind of odd. Fritz, you remember when we were working on that when we were working on our GTO last time, last class? We would manipulate those field trims. We would create it lean or rich, and our short terms would ratchet down slowly until it brought that sensor back to switching, right?
That's right.
Okay, but then like maybe 10 seconds later, our long terms would react, right?
Yeah.
It was relatively fast that our long terms were reacting.
Yeah, a little faster than this one.
Right. What I'm seeing with these air-fuel ratio or wideband sensors is our long terms are taking a little bit more time to adapt. It's just kind of something that I've been watching and noting. And I don't really have an explanation for it yet, but I'm working on it. I want to kind of know why it's taking longer for the long terms to adapt. Kind of odd.
Good question.
Kind of odd, because I mean, really, we ran that thing lean for quite a while, up around that 14 mark, and our long terms never really did anything.
Yeah, that's true.
So maybe it's because the short terms are allowing for more fuel correction, and it's trusting the short terms more. Who knows? I'll try and find the answer for you guys and get that to you by our Tech Connect at the end of the month of why it takes longer for those long terms. Alrighty, so this thing's still idling. Let's should we show them the heater circuit?
Sure.
Okay, so say for whatever reason you guys don't have your scan tool at home. Okay, you can't look at data. You can't look at engine data. You forgot your scan tool, but you happen to have a lab scope. I don't know. I don't know who has that situation, but say you happen to have a lab scope or even a multimeter with an amp clamp. Okay. You can do this test on here to at least verify that the heater's functioning, right? Because that's, again, the necessity. You have to have a heater in order for the circuit to function.
That's right. Okay?
So for you guys out there that answered the question already, I'll give everybody one more chance to answer that question if you want to, if you want to amend your answer. Okay, so I'm going to bring up our heater circuit on the screen. I have channel C here is going to be our heater's voltage, and I'm actually probed into this wire right here. This will be channel C. This will be voltage on our heater circuit. And I would expect to see our heater probably operating around battery voltage, so I'm going to grab a 20 volt swing here. And I'm going to bump this up a little, bring our 0 mark to a level line somewhere. There we go. Okay, so we're right at 0 volts right here. And oh, we're really zoomed in. I'm going to back this out a little. And there we go. Starting to see more. Let's back it out just a little bit more. And there's our heater circuit, okay? So I'm going to throw a trigger. I'm going to move my trigger over to channel C so I can trigger on my heater. So this is my heater voltage, okay? So we're sitting at battery voltage around that 14 or so mark. You know, it's charging system voltage. That's normal.
That's normal.
And then what happens? Well, pulse width driven, the computer grounds the circuit, right?
Yep.
It applies that ground, and at this point, which is not exactly down to 0, just make note, this is still a floating ground on this heater circuit. We're around 0, this is showing 1 volt here. So it's still a floating ground, so it drops it down, and at this point our heater is on, and then the pulse width turns off and our heater shuts off. So you could do this with a voltmeter, you could do this with a scope. It's easier to see on a scope, obviously, because you can look at it over time. On a meter, you might have to use your frequency setting on there to read the hertz of this wave. That might be able to tell you something. Let me throw in the amp clamp now, and I'll show you guys the amperage on this. Now, I got to turn it on to a current clamp. And let's start at 5 amps. And judging by the little exclamation point here, we are over 5 amps. So I'll jump to 10. And there we go. All right, I'm going to bring this down, and I'm going to actually bring up our voltage so that you guys can see the difference here. So just like we were just talking, Fritz, we started at high voltage, right?
Yep.
Computer grounds the circuit. So the computer grounds it, we have a path for electricity to flow. So when our electricity flows, what happens? Our current flows.
Yep.
Our current flows, and we keep the sensor hot. And this is happening multiple times per second. Remember here, we're looking at 100 milliseconds per division. So that means that we're looking 1, 2, 3, 4, 5. I believe this is 10, so we're looking at 1 second right here. So this is happening 1, 2, 3, 4 times per second. This heater's being cycled on. And if we mouse over this, we're currently reading roughly about 6 amps to run this heater. That's quite a bit of load. That's 12 amps just between 2 sensors.
Yep.
I mean, that's quite a bit of load on this system. Say this alternator only puts out, I don't know, 80 amps maybe, 100 amps?
Probably so, yeah.
120 maybe, I'm guessing here. But that's quite a bit of load on these electrical systems. And you'll see, remember this is a 2003, you'll see we're going to do a 10-year bump here. We're going to see that amperage drop quite a bit because of new sensor technology that was developed. So 6 amps on an old sensor is pretty normal. And I'm saying old being a 2003, it's pretty normal. It took a lot of amperage to keep these things up around that 1500 degree mark. Okay? So you can use an amp clamp for this, and you should read amperage. Now remember, if you're using a voltmeter, it's going to average your readings. So it's going to average that time that it spends at 0 and the time it spends at 6 amps. So even though you might have a good sensor reading, that 6 amp reading, your voltmeter might only display it at 3 amps or 4.5 amps, depending on the pulse width duty cycle of that circuit, okay? So don't get fooled by that kind of thing. Pulse width controlled circuits can really throw a meter off because it's having to average that number, okay? So don't get busted by that. Your best bet's probably to throw a scope on it.
Yep.
If you forgot your scan tool at home and you can't watch the voltage. Your best bet still is scan tool, look at your voltage or whatever the computer happens to be giving you at that point. Okay, I think we're done with the Lexus now. Let's shut that off, and we got to transfer over some stuff to our Taurus. So I'm going to grab the scope leads and disconnect everything here and try not to drop anything. All right. And again, guys, if you're not familiar with what scope we're using, it's from the wonderful Pico company sent us this scope, so we're using this thing, and honestly guys, I am loving it. It has done everything I wanted to, and we're able to show the scan tool and the scope at the same time now for you guys, so I think that's really, really beneficial. Okay, you're getting the scan tool transferred over. I'm going to get this all hooked up. Dave, could you bring up that picture under the hood of this thing? Thank you. You guys can see I got some blue connector leads up there and my amp clamp already connected on this side. So I'm going to show you guys what exactly these connectors are in just a second. I want to get all my leads plugged in, and I'll show you where I'm hooking up on the wiring diagram in just one moment here. And then you can go ahead and turn on the key if you'd like, Fritz. Perfect. All right, let's plug this guy into the scope. So now I have 4 voltage leads hooked up, blue, red, green, and yellow. I have no amp clamp connected at this moment. And then I'm going to bump this guy onto our ground setup here, and everything is going to chassis ground. Remember guys, when our sensors are hooked up in their circuit, they're not using chassis ground. So all of our voltage values right now are going to be based off of chassis ground, but I will show you, and just stay tuned, I'll show you where I'm getting with that. Okay, now let's talk about this first. These are those leads that I was talking about. Dave, could you bring that picture up just once more, please? So there you see those blue leads right there with those probes on the end. This is what the lead looks like. It's kind of nice for doing things like this, where I want to keep the circuit intact, but I want to be able to measure without back probing. It's a pain in the rear to put 6 back probes into a connector and cross your fingers that they don't touch. So these were in our picoscope kit when we got it. I'm sure you can buy these out separately, but they're a male connector on one end and a female on the other end. And terminal sizes and stuff differ between the color of the wire. I have the blue ones on there because they match our Ford connector. Black one here, I got green, yellow I believe, and they're all gonna just change the thickness of the terminal. But I can hook up in series now and then throw my scope on here. Excuse me, maybe not in series. I can keep the circuit intact and then monitor the voltage with the scope, okay? So I don't have to do any sort of intrusive testing. I don't have to back probe these. I'm able to keep the entire circuit intact, and that's imperative again for these wideband sensors, because if I were to disconnect the sensor to check values, I just killed my heater circuit. My sensor's not going to function anymore, okay? So that's where stuff like this does come in handy. And I'm sure maybe if you go out to AES Wave or something, they might have things like this out there. Alrighty. So what should we start with first? Should we look at scan data first and show them show them the plethora of PID information we have on this car? And then actually, I'd also like to show that generic data on this one. In our last class, a viewer came on and mentioned about using generic data instead of vehicle-specific data. And I didn't get a chance to play around with it in between classes, so let's just do it live and hope I don't look like a fool. As I'm standing in the middle of the screen. All right, you got the key on, right?
I believe so.
Should be good. I think we're in. So I'm going to go generic functions, and I am going to go to, maybe I can't get generic live data on here. Onboard monitored systems, maybe. Let's see what this tells me. No communication. You want to wiggle that connector around?
Yep. I know Jim uses his car for a lot of testing, so his OBD2 is a little wore out.
Yeah, maybe we got to get a new connector on here. All right, let's see if it works now. Nope, still not.
Okay. What's that?
Nope.
Nope.
You're just having some bad luck, huh?
I guess so.
And okay, maybe it's that it's not going to allow me into this function. Let me just go back to regular data and see if we can get that. Still no communication.
Okay, let me try it again.
Yeah, go ahead. Sorry about this, guys. It was working just fine, but the problem is of course, being live, things like this can happen. I think the
How's that, Mike?
the data link connector pins are a little spread on there. No, still no luck. Let me take a peek here.
I got a little tighter now.
Yeah?
Well, there we go. It's a little tighter.
Okay. Sorry guys, we'll get it. Maybe? No.
Nope.
Here, let me take a look once.
Yeah.
I know this thing is finicky. All right. Connector's clicking. There we go. Now let's see what we got. Do 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 do. Come on. All right. Well, maybe I can't show you guys data. I might just have to go with the scope on this, which is going to completely kill it because we need to use data to diagnose these things. Did maybe the key fall out of the connector?
I don't think so.
All right, I'm going to fire it up.
I'll be watching the screen.
It's not going to.
Yeah, okay.
Hey, there we
There
go.
we go.
I think we're in. All right. So I'm going to go here, get out of the way. And we got live data. Maybe. All right. So first of all, guys, you can see that I'm in scanner, engine, fuel trim, O2 sensor data, and we have a ton of information in here. I can even, look at this. Look at all this. I'm not even at the bottom yet. Okay? So you guys can tell that there's a lot of information on these vehicles. Okay? So I'm going to actually just go ahead and create a custom graph. I'm going to take everything out of here, and I'm only going to select the things related to Bank 1, Sensor 1, wideband sensor. So let's go through this. Bank 1 EQ, or ER, equivalence ratio, we'll take that. This one could be tricky right here, exhaust gas oxygen sensor, okay? Remember, this is our oxygen sensor here. Some people get thrown off when they see exhaust gas first, they're thinking EGR. Well, we gotta remember that Ford likes to call things a little differently. This is an EGO sensor, or also known as a UEGO for universal exhaust gas. So we'll take that, we'll take this. Let's see what else we got. Heated sensor, we'll take that. We'll take that. Heated command, sure, why not? And again, guys, I'm just going through here and clicking anything related to Bank 1. I'll take some fuel trims. Bank 1 sensor 1. So we'll take this one, we'll take that. Sure, we'll grab all these. Sure. So you guys can tell as I'm going through here, we have quite a few PIDs, and I'm probably missing some as well. But this is just a brief, quick grab. Let's throw them in list, and let's see what we got. All right. So first of all, at the top, our equivalence ratio. This thing is desired to run at 15:1 currently, so slightly lean, slightly over that 14.7. Our actual equivalence ratio, our lambda, is currently sitting at a 1.02, and of course I said something that bumped down, but it's right around that 1 mark. And here's where the difference lies between our Lexus and our Ford. Our Lexus was giving us voltage that was varying. Our Ford, like we talked about in the beginning, is going to give us amperage variance. Okay, so we're looking at our milliamps. So this is 0.038 milliamps. Okay, super slight amount of current flowing on here. But we're at this very low amount of milliamps changing dependent upon the system. There's our short-term fuel trims down there. Somewhere on here was here's our long-term. We're sitting right at 3.9 positive, so we're still in percentage. We're adding a little bit of fuel, so this thing's running slightly lean. And then we have some statuses and activity. We got O2S11 status, no fault. So that's kind of nice to know that it says there's no fault with our sensor. Okay. I'm going to go ahead and grab some of this information. I'm going to take some of this out. because what I want to look at is I want to go into graph mode, and I just have too many things right now. I'm going to take out desired. I'm going to take out our heater stuff. I'll take all these out. I'll leave long terms. I'll take that out. Here, this is interesting. There's trim resistance, circuit resistance, and ohms right here. This is the computer monitoring our trim resistance on our circuit. Take that out. So I'm going to take all this stuff out. Now I'm going to be able to come up with some graphs that hopefully make sense. Okay, long-term field trims, short-term field trims, our actual real-time lambda, and our current in milliamps of our sensor reacting and pumping oxygen. Okay, Fritz, go ahead and pull that hose off of here, and let's see how that milliamp reaction happens here. Okay, so we pulled off the hose, so we got a little bit of a vacuum leak going on, and hardly any change at all. Okay. So it is sitting a little bit higher now. Why don't we feed some fuel into that? And we should see this thing change. We should see our short terms probably go negative, right? Because we're adding fuel. There they go. So our sensor dropped down, and now it's starting to respond, and our short terms reacted. All right, go ahead and pull it away. And we should see the thing all of a sudden run lean. Look at that, now it's running lean, it's reacted. Our milliamps jumped up. So that right there is telling me that when milliamps on this engine are positive, it's running lean, and when they're negative, it's running rich. Okay, so this is pretty normal running. This is a normal running engine. Now let's look at what this is all going to show us on our scope. All right, so I got the scope up on the screen here, and as it sits, I am probed into the 4 of the probes here. I'll show you guys where I'm at. I am in, go ahead and zoom in again. So our blue trace is going to be on pin 1, pumping current. Our red trace, channel 2, is going to be on pumping current trim. Our green trace is going to be on our ground reference. And our yellow trace is going to be our UO2S11 circuit, okay? So let's take a look at what we got. Looks kind of like a mess. Well, first of all, we're not using a current clamp anymore, so I'm going to throw this back to a standard old voltage clamp. I'm going to move some of this around. And let's see if I got, okay, so I'm going to make sure I have active filtering on everything. Try and clean up our lines. And okay, so what are we looking at here? All right, blue and red first. We'll look at those. So right now, blue and red are both, here's 0 volts in blue, here's 0 volts in red. They're exactly the same on top of each other. I'll move it up a little, there we go. Now you can see them both. They're mirror images, okay? Which is, when you think about it, it actually makes sense, because what are we doing in that circuit again? We got that trim resistor in there. I'm gonna bring this back up. We got this trim resistor circuit right here and our pumping current circuit. They're both doing the same thing. The computer's watching them both, and they're both mirror images of each other, okay? So I'm gonna lay them back on top of each other where they belong. And let's look at now trace number 3. Now trace 3 was our green, which is currently sitting at 2.45 volts, or just under 2.5 volts. And green was on this pin right here, ground reference, which makes sense. If you remember back from that slide, it was 2.4 to 2.6 volts on this one. Perfect. And our yellow is sitting currently at just over 3 volts. All right, well, what is this telling us, guys? This is sitting at just over 3, this is sitting at 2.4. What happens when we do that math again? Comes out to that 0.45 millivolt mark, right? Just like in that slide that I had, where the computer's watching the nerd cell, looking for that 450 millivolts. That's what we're actually seeing here. But remember, like I said before, all of our grounds right now are off of chassis ground. what happens when I use the actual sensor circuit ground. Watch what happens to our yellow trace. Our yellow trace is going to move, okay? So watch, I'm going to hook it up. So I'm going to disconnect ground on yellow. All right, so ground is disconnected right now, and I'm going to hook it up into our sensor ground, okay? There we go. And we saw a drop. And I wonder where we're at. And now channel D, we should be at. Let me bring this down. Actually, I'm going to go ahead and zoom this in now because we're a lot lower on our voltage level. We'll come in even more. And I think I might have told you guys wrong. I think I need to hook into a different wire. There we go. Let's try that one. That looks better. All right, so you got to make sure you have your connections right. But once you have your connections right, look at what we got. 450 millivolts. And in fact, I'll drop this down to 500. So 0 to 500. And I'll get as close as we can here. 450 millivolts on our yellow line. So that is our nerd cell being monitored by the computer at that 450 millivolt line. Now Fritz, could you do that again where you adjust, that you pull that hose off and we see our short terms react? Could you do that again while we're watching our 450 millivolt line?
Oh, right now it's off, Mike.
Oh, okay. Go ahead and install it. And we see a little bit of reaction in our short terms, but we're still at that perfect 450 millivolts right here. And go ahead and pull it off. And again, we're going to see a reaction in our short terms. Maybe. It's not a huge vacuum leak on here because it's just a breather hose. So go ahead and run some fuel into there, Fritz.
Okay.
And we should see our reaction. But I want you guys to really pay attention to that 450 millivolt line now. All right, we're getting somewhere. Look at that, she's dipping. 7.7, negative 10 on our short terms. Our sensor's down under 100 milliamps negative. But guys, look where we're at. We're still at 450 millivolts. All right, you can cut it. And eventually here, as that fuel is all used up, it'll go back around that 0 mark. But our 450 millivolt line still has not even wavered a little bit. Okay, that's how fast these sensors are able to react to changes in the air-fuel ratio. So that's why we're able to get such really, really good emissions out of a 4-cylinder turbo motor in 2013 is because, guys, we're almost real-time reacting to changes in our fuel trim, okay? So this 450 millivolt mark should always read that, 450 millivolts, period, end of story. But you gotta remember that you're not using chassis ground. You need to use this reference ground that's on this wire right here. So I have one lead right here with my ground lead hooked up right here, okay? You gotta use your reference ground if you happen to be checking that 450 millivolt mark. But chances are, you're probably not gonna look at that. The other thing that I wanted to call out was this channel A and B right here that are moving. You guys probably noticed when Fritz ran it rich or lean that it seemed to move when he ran it rich or lean, right? It seemed to fluctuate. And that is fluctuation in that line. That is that current pumping line that's coming from the PCM. Now, I don't know that we can really track that and say that's one way or the other because that's not the way the computer's measuring it. The computer's measuring it in milliamps. That's going to be the best way to diagnose this thing. Use a scan tool. It's going to be the best way. It's really going to be the only way to diagnose it, okay? So look at your live data and diagnose it with that. Now, I wonder, since we got it working now, let's back up and see if we got any generic data on here. I'm just curious to see what it looks like. I don't know if this is where I want to go. Again, I didn't practice this, guys, but I figured it'd just be worth a quick look. Maybe. Or maybe not. Because nothing is quick with this thing. Oh, man. Okay, so these are our mids, bank one, sensor one. Let's see what this looks like quick. I think this is just going to be our test parameters. Yeah, this will just be our test parameters for this thing. I don't know that it's giving us any live data. Readiness monitors, freeze frame data, onboard systems, request control, calibration, in-use performance tracking, and VIN number. I don't have any sort of generic data. Let's go back to data display once more, throttle, yeah. There's no sort of generic viewable data for this vehicle, unless I'm doing something completely wrong, but I don't see any. Okay, let's do the amp clamp on here. I want to show you guys one more thing with the amp clamp on this vehicle, because it's a little bit different. So I'm going to go ahead and turn this on. She should be zeroed out. And I'm going to take channel A here, and I'm going to go on to our green connector. So again, we're going to look at our control circuit as well as our amperage. All right, so I'm using, let's hook up our amp clamp to the scope. I'm going to pull these other channels off so we can get rid of them. Hook up our amp clamp. All right, there we go. I'm going to take off these channels here. And we need to tell the scope that we're now using an amp clamp. We're using a 60 amp current clamp in the 20 amp mode. And our heater circuit again is probably going to be battery voltage, so I'm going to bump that up. And we got a mess here, or it looks like a mess. So why don't I go ahead and zoom in a little bit. There we go. And where is our amp clamp? Ah, there it is. All right, you guys see this? So right now I'm on that -5 to 20 amp scale, and here's 6 amps. Remember, with our Lexus, we were way up here. I have to bring this thing up to get our amperage. So I'm going to actually shrink down our scale here. I'm going to bring it down under 5. Look at this. Look how different this is right here, guys. In fact, I could bring this even lower, because right now we're sitting at 1.5 amps. So let's bring this down to 2. There, now you can see full screen. Let's go in a little bit more. Maybe one step further. Now you guys can see full screen. Here's our voltage. So we're at 14 volts, down to 0. And let's bring this down a hair. Trying to get this 0 line lined up. Okay, so here's 0. And the clamp doesn't look like it's zeroed. So let me zero that so I can get an accurate reading. There we go. We'll bring it back to 0. Hook it back up. Uh-oh. I just killed the circuit. All right, let's put that back on there. Okay, so now we're actually reading 0. We're very close to 0. And 1.6 amps. So what a huge difference, right? 6 amps on our Lexus, 1.6 amps on our new Ford sensor. So changes in wideband technology over 10 years really afforded us a easier sensor on the engine's electrical system. It's requiring a lot less amperage to maintain that high temperature. Now, what happens when the heater circuit drops out? This Ford here is kind of unique in the way it reacts. This thing is always going to be looking for that heater circuit. Go ahead, Fritz, and kill the power to that. Now, unfortunately, we can't just pull the fuse.
You ready for it?
1 second. We can't just pull the fuse on this because it powers up our bunch of different stuff. I'd have to look in the diagram again. VCT, both VCTs, purge, vent, and the bank 1 sensor 2 sensors. So it's powering up a bunch of stuff on this fuse, okay? So we can't just pull the fuse. So Fritz is going to go ahead and disconnect the wire. And we should expect to see our current drop out because an open circuit, we're not supplying power. There we go. Current dropped out, but look at this. Look at our signal circuit. Look what it's doing right now. This is that pulse width ground control right here. Look at that. I'm going to move our trigger down so it stops bouncing around. Maybe down a hair more. There we go. So now it's nice and steady. But look at this, guys. Look at this wave. What are we looking at here? We're at a 0 to 3.5 volt line right here. Going back and forth. with the circuit open. What's happening right now? It's kind of crazy, right? The computer is actually hunting right now for that circuit. It's probing right now, looking for that heater circuit. And now it's not gonna supply that same, it's not gonna do the same thing. It's not gonna ground out that same amount. It's not gonna apply any vast amount of power to it in case there's something shorted, so it's kind of protecting itself, but it's still looking for that circuit. It's looking for continuity across it. It's looking for that heater to be there. So the second Fritz hooks this thing back up, it's going to respond, and it's going to bring our heater right back. Instead of it going into limp mode, instead of it completely failing and our sensor going dead completely, it's still looking for it. And actually, let me just show you guys what happened to our sensor. Hopefully our custom data graph is still on here. Cross my fingers that it is. Maybe. Beautiful. And let's throw this into graph view. And look what we got now. Our lambda PID is zeroed. Our short-term field trim PID is zeroed. Our current PID is, for some reason, at a negative 0.038. Maybe that's where the sensor was unplugged. Maybe that's where it was sitting. So Fritz, why don't you, once we get the lab scope up on the screen here, I'm going to have you hook this thing back up. So let's bring them both up on the screen, and you guys are going to be able to see them react. I'm going to move this up. Grabbing the wrong one. Move this up. And I'm going to bump this back down a little bit because I would expect to see this voltage jump again. I don't want to move it too far because I want you guys to be able to see it. All right, Fritz, go ahead and hook it up. Look at that. And I'm going to bring it back down to that same time division we were before. Look what we got, guys. It's right back to functioning. We didn't key cycle it. We didn't clear anything out. We just opened up the circuit and then closed it. And look at our reaction out of our sensor. It's back. It's back to functioning just like it's supposed to be. So this computer was looking, it was probing, it was searching for its signal. It found the circuit and went back to field trimming like it was supposed to. It went back to working just as it was designed to. Okay, so this is possible in newer vehicles. So watch out for intermittent faults, really, because the computer's able to make up for it if that problem does come back. It's not going to be a hard fault. All right. Well, Fritz, I think you can shut it off. I think I showed everything that we wanted to. To just sum it up real quick, guys, you need a scan tool. Unfortunately, to diagnose a wideband sensor, you almost have to have a full function scan tool that has data graphing ability, because otherwise you're just going to be wasting your time. I can't think of a different efficient way to do it. You know, to measure down into the milliamps. You could maybe hook up an ammeter in line and maybe see something, but we're talking down in the below 1/10 of a milliamp.
Way
I mean,
too
it's
fast.
very, very slow, or very, very small and very, very fast.
Yes.
So scopes are okay for looking at the heater circuit if that's all you have, but a full function scan tool to look at it the same way the computer does. Remember, when we're looking at trouble codes and diagnosing for faults on a system, we need to diagnose the same way that the computer does. Otherwise, what was the point in diagnosing, right?
That's right.
We want to follow the exact same way the computer tests it. We want to do the same thing. Okay? Holy cow, it's already 3:30. All right, let's see.
Yeah, I'm kind of thirsty.
Let's see what you guys got for comments. This one ran a little late. I'm sorry, guys. I hope you're all still here. We got a bunch of comments here. So people answering the question. The question was, again, that the Tech A said that the heater being failed doesn't affect the sensor's operation. It would just take longer for the sensor to heat up and by using the hot exhaust. Well, I think we just proved that with our Taurus, that with that heater not functioning,
It's not going to work.
it's not going to work. The sensor's not going to function at all. Tech B said the sensor will not function at all with the heater and needs to be without the heater and needs to be replaced. Well, Tech B was definitely right. All right, so we did get a couple people to change their answer. Looks like Mace and Ron both had it correct before I gave them the option to change their answers. So congrats, guys, on that. Mike looks like he's changing to B, so good. It looks like you paid attention. Jim as well is amending to B. Awesome. I was wrong. So the Varus hates low voltage. So Sandy's saying the Varus hates low voltage, and that's probably what it was. When we started it up, it brought the voltage back up. And May says no mode 1. That's strange. It is strange. I was kind of expecting to see mode 1 in there with some sort of data, but it wasn't. All right. My email address is right here on the screen, guys. For all of you that got it right the first time, or the second time I'll give it to you, go ahead and shoot me out an email with your mailing address, t-shirt size, and the color of your shirt, either gray, black, or blue, and I'd be happy to send one out. JJ Toms, you can only get 1 shirt per day. I know you were on the first one. You already sent me an email, so thanks for trying again, but I tend to remember names of, of people emailing me, so only 1 shirt per day. But thanks for joining us on the second class. I think that's about it. Check us out on social media, Facebook, Instagram, Twitter. Search for Wells Vehicle Electronics. We're updating those pages constantly. And for those of you that are watching on our Wells VE YouTube channel right now, we are transitioning things over to the Wells Vehicle Electronics channel. That is where you're going to find all of our most recent Tech Connect episodes, as well as our most recent Counterpoint episodes. So if you are looking for those, you're going to have to head over to our Wells Vehicle Electronics channel. So if you haven't been there, please check it out, subscribe. It's going to be the same live broadcast. We just happen to be transitioning over to that channel now, okay? So thank you guys for being there. Really appreciate you sticking with me for an hour and a half. Holy cow. I'm out of breath.
Yeah.
So, okay, guys, we'll see you April 6th. This is our next class. We're going to be finally fixing up the GTO and showing you guys some tips and tricks on how to diagnose rich and lean conditions. And we'll see you then, April 6th, 11 a.m., 2 p.m. Central Time. So thanks for sticking with me, guys. We'll see you next time. Thank you.